Alright, guys, it seems to be about 1 o'clock. I think I'm gonna go ahead and get started here. Let's see, I have a few announcements today as we kind of get rolling. This is our last regular week, if you can believe it. So we are gonna be done and out of here basically a week from now. And so there's a lot going on though in the next 8 days, as you can probably imagine. So first thing is, I passed back the exams. They were, the in-class part I thought was pretty okay. The sort of normal, what I would expect. But where there was the biggest problems, to be honest with you guys, was really the take home. A lot of people took some stuff home, and of course, I expected the take homes to be very easy for me to grade, but unfortunately, they were not. For some people, it took me quite a bit of time. If you're taking home something that's directly out of the book or out of the notes or out of the definitions or something, all you got to do is pull those up and write it down. Just copy it down, turn it in. Some people didn't do that. So it turned out to be, most people did not exactly have a field day with the take home part. So that did not help people as much as I had hoped. Nonetheless, there were some very good scores, as there were with all of the exams. There were some people in the 80s and 90s again. So I feel like it was reasonable. I actually thought I kind of liked those questions for the most part. So definitely take a look at the solutions. I put a copy of them into the midterm 3 resources folder. I don't want to go over the exam in class because there's always a certain subset of people who already got those things right, and I don't need to waste time on that. But if you look over your exam and you have any questions for me, you want to check with me about it, definitely feel free to stop by my office hours for that. And I'll be glad to go over it with you or clarify it or whatever, but you should definitely not just let it go. But anything that you didn't quite figure out for this exam is probably something you should look back to again and just make sure that you're solid on it by the time you go over it. So that's with the midterms. Your grades should be now kind of up to date in Canvas. If you have any questions about that or about your class standing or my advice or what I would recommend in these last week or so, you can always come talk to me about that as well during my office hours. I will not be able to obviously have a crystal ball as to what will happen, but I will also do my best to be as encouraging and positive as I can. I don't like to turn those into negative sessions. We can have a private one-on-one session. If we can do it in Zoom, we can do it in person. If you just want to kind of know, where are you standing going into the final and what maybe I would have for advice. And I'll definitely do my best to tell you what I think you should do. So that is that. So that's the midterm. Now, for this week, we have 2 homework assignments, one of which is due tonight. I'm going to try to save a few minutes to help with some of these problems during our class today. I mentioned, I think in my weekly email, that I have another exam to give in my other class this afternoon. And so I'm not going to have my office hours tonight because I need to go do a furious grading session to get those done by Thursday. However, what I did realize is that I'm going to be sitting there for 4 hours with nothing to do while I'm proctoring this exam for my other students. So if you would like to talk to me later today, you can do that between 4:15 and 7:45, as long as you just come over to MH 476. I'll just be sitting there in the front. We can go out in the hallway and just talk about something if there's anything on the homework. If it's not urgent, I'd probably prefer not to do that. But if it's something that would be helpful, if you're trying to get the homework done today and you really don't have any other chance to ask me, I would do that. Because at 8 o'clock, I am going to leave campus. I'm going to go off and I'll be gone grading papers probably for the next 24 hours until Thursday. So anyway, but that is another, I forgot about that I am just going to be sitting right next door for 3.5 hours, and I could certainly help you at that time. Okay, so that's the homework that's due tonight. There's also an assignment that will be due on Saturday, and on that one, it's going to be based mostly on stuff we're going to do this week, especially today. So if you haven't started that yet, obviously that makes sense that you'll need a little bit of time And on Thursday, I can help take some questions on that aside. So we'll get you guys squared away. Those are the last two homeworks. Forgot the homework for sure. Our final, let me just say a couple quick words here about this. Our final exam is going to be on Tuesday next week. So that's May 13th. And it will be in our regular class hours from 1 to 3. I would like to try to give people a little bit of extra time. If anybody has another final, like right at 3, so that I can try to make a little bit of an arrangement to give you a little extra time. Not that I'm planning to make the exam really longer than any of the midterms, but I just feel like I hate for time to be the reason why people get into trouble with these things. So I might just try to push this a little bit, just kind of, I don't have anywhere to go on Tuesday at 3. So that would be not a problem for me, but if it's a problem for you, let me know and I'll try to figure out a way that we could work that out. It will be a comprehensive final. And I did put together a review packet, a resources folder. And just this weekend, I updated it. There's a sample final in that folder. There is also a review packet in that folder. That's kind of what the review packet basically says is go back to the review packets for the 3 midterms, right? I mean, that's already a ton of stuff. So it doesn't have a lot to it there. There are some practice problems though in that review packet. Some of which I may use during the review sessions. So I'm just going to do some review sessions. Let me just jot down some times here. So on Saturday, I'm going to do reviews from 1 to 3. And then on Monday, I'm going to do a review from 2 to 4. So just like with the midterms, I'm going to do a couple of sessions. I'll do these outside of my office again. At least that's where we'll start off planning to meet. And I'll record them and send them out with YouTubes like I have for all of the midterms as well. So I might be doing some of the problems that are in that sort of slew of practice problems during the review. But otherwise you can try them. And I did type up the solutions to all of them, so you can always just read the solutions and make sure that you're following along with all of that. Okay. Let's see. The midterms that we took, in each case, I let you guys take something home. Of course, you know that. And so you had this option to like spend 36 more hours and then turn something else in. I'm not really allowed to give you like homework during finals week. You're supposed to be able to just focus on your finals. So I am not planning to do a take home part to the final. I may give you some choices on the final that do this or that kind of thing. But the other thing I am going to do that is a little different than the midterms, and this will be sort of making up for not having any take-home part, is that there is going to be an explicit proofs section. So what that is, and it's already in Canvas, as I put it in there a few days ago, there is a list of theorems. I think there's 7 of them. And I am going to pick 5 of those 7 to put on the final. You will then choose 3 out of those 5 to actually write up during the final. So that's quite a bit, because the proofs that are there are fairly, they're not just the little teeny ones. They're the ones that are going to take, a paragraph to half a page anyway. So because of that, I decided, well, this should be a pretty substantial part of the exam. So I'm putting it at 25 to 30% roughly. So that's a pretty big chunk, in terms of getting your overall percentage for the exam up. You want to nail this part, right? You don't want to be losing points on this, because if you lose points on this, then you put even more pressure on yourself to get the other things completely right. And the other things, you're going to have to do it on the fly. You're going to have to be creative about it, right? This is stuff it's coming. It's coming. The other thing I'm going to allow you to do with this proofs section is I'm going to allow you, if you want, you don't have to do this. You can just come do it during the exam. But I am going to allow you to do the proofs section during my office hours before the exam. You can't do it after 3 p.m. on the 13th of May, we are done, right? But I will allow you, I'm gonna have office hours, obviously I've got review sessions, office hours, I'm gonna be in every single day, pretty much. I'm not going hiking this weekend. I'm gonna be around pretty much every single day with office hours. And so you're welcome to come in and you can say, I wanna do my proofs now. And I will let you do that ahead of time so you don't have to worry about it. Having said that, I am gonna be writing an exam where within this time frame, I think you can do these proofs. So if you don't wanna come in special, you don't necessarily have to do that. If it's a hardship to come in, you would like to do them early, but it's a hardship to come in because you don't wanna come in on the weekend or whatever it is, let me know. I might be willing to even let you do this remotely, but with my supervision. So you'd have to check with me about that. So you can let me know if that would make it easier. But if you're coming to the review sessions, it would be a reasonable thing to do these sometime around that time frame. So you're gonna have to study those proofs a little bit. It's not just about memorizing them, it's actually about understanding them, because if you don't understand them, it's hard to reproduce them completely from memory. There's enough meat to all of these proofs that it's, I mean, even for myself, if I don't understand something and I just sort of superficially try to memorize it, it doesn't take me very long before I'm in over my head on that. So I definitely would recommend that you take the time you need to learn the proofs and understand them. Does this make sense? It's kind of how I would like to do this. So again, it's optional to come in and do them early. If you don't come in and do them early, you should still have time to do the whole exam, especially if I give you a little extra time at the end. But some people just like to kind of get that done and have that off of their plate. Okay? So any questions? Yeah, Danny.
What percentage is the final?
For the whole grade of the class, I think it's about 30%. Something like that. It's a fair bit. It might be about 30%. So remember also, I have not done the re-weighting of your grade yet. So whatever it says you have as a grade right now in Canvas is underestimating your actual grade, because after the final is over and I've got everything done, what I do is I go through it and say, okay, what was their best thing? Was it the homework? Was it one of the midterms? Was it the final? And I make it count an extra 5%. So if your final is the best part of your grade, then I would count it for 35% of your grade instead of only 30% of your grade. And what I do is I take that 5% away from whichever of these parts of your grade was the lowest. So if one of your midterms was your weakest part of your grade, I would make it count 5% less than what it says in the syllabus that it's going to count. So what that ultimately does is it tends to, my shoe again, I know he's looking at me like he needs to fix his shoe. What that does is it effectively will add about 3% to your grade compared to what it says online. So it's roughly where you're at as of right now. So anyway, so that's where we're at. If you got any questions about your grade, if you got any questions about the final or advice, or you need anything like that, just let me know. You can stop by today and see me next door, or the rest of the week through the office. I sort of took a personal day yesterday. Got my oil changed in my car. Got a whole bunch of laundry done. A whole bunch of things I had to do. But now I'm good to go. So you will see me around a lot for the next 7 days. So that is my update. Okay. Well, we were in the middle of a proof a week ago. It's been a few days, so I'm going to call your attention to this, and then I think we'll use this result to do some of the homework. This is a theorem that I mentioned last week on Tuesday. If we have a Riemann integrable function already, and we move a finite number of points on that function, so we just tweak it a little bit, and we make a new function g. So g is a new function where we've taken f, which is already Riemann integrable for whatever reason, and we tweak a finite number of those points to make a new function g, then g will still be Riemann integrable. And the value of the integral won't change either. Okay, so the integral of G will equal the integral of F. So that's kind of nice that you can play around with a finite number of points without affecting anything. And so this is theorem 6.5. We partially proved this a week ago, but I ran out of time. So I just want to remind you, oh, I ran out of time. I have that here somewhere. Yeah, I forgot. I have a bunch of proof strategies for your exam. I want to share these with you here. Running out of time is always a good one. A great excuse. So feel free to grab. I wouldn't recommend using these on the final, but just in case you are curious, you know, I try to use a few of these. I kind of like the proof by intimidation, but anyhow, somewhere on here there's a proof by lack of sufficient time. Because of the time constraint, I'll leave the proof to you. Yeah, so I'm real good at that. So these are kind of funny. I found this a few years ago and just decided to print it out. So we'll see how many of these I need today. Hopefully not.
Hopefully
too many.
none.
Hopefully none, yeah. Hopefully none, but if I get desperate. What's that? That's right, that's right. So I might get desperate here, we'll see. Okay, anyway, yeah, so I ran out of time to finish this proof, but let me tell you where we did get with the proof so you have an idea. We got the first part proved last time. We did prove that G is Riemann integrable. Okay, so given that F is Riemann integrable, we proved that G is Riemann integrable. Now, how did that proof work? Well, as we often do, to prove that a function is Riemann integrable, we use this theorem 6.2. This is the one about, you know, for all epsilon greater than 0, there exists a partition such that UPF minus LPF is less than epsilon. So what we did in this proof is we said, all right, we're trying to prove that G is Riemann integrable, so let's let epsilon greater than 0 be given. Now, we have to come up with a partition at this point. But the thing is that we already have a partition for F, because F is assumed to be Riemann integrable already. So that means that there's already a partition where UPF minus LPF is less than whatever I want to put here. And as we saw last week, the thing we need to put here is actually epsilon over 2. Okay, so we can do that because F is already Riemann integrable. Okay, ultimately, as you can see from the bottom of the proof, when we get down a little deeper into it, we ultimately want to prove that UPG minus LPG is less than epsilon. That's ultimately how we're going to win the proof, right? So, but we have to start with F, because F is what we're assuming is Riemann integrable. So we know that UPF minus LPF is less than whatever we want. I'm going to choose epsilon over 2 here. And then I didn't write down all of the details from a week ago where we had to refine this partition. Remember, when you refine a partition, you just throw more points into it. It only makes the difference of the UPF and the LPF smaller. So you're certainly still going to have that same inequality. But that refinement was chosen in a way to make, see, because F and G only disagree at like a finite number of points, you can sort of tweak your partition so that the places where the F and the G disagree have very, very small delta xi's, right? And because of that, you can set it up so that the UPF and UPG are very close to each other, as close in fact as you want. So I did this last time, and we said we made a refinement that would put them less than epsilon over 4 from each other. And then same thing with the LPF and LPG, right? Normally you have 2 different functions, their L values would be completely off the charts different, right? But because F and G are very similar, they only disagree at a finite number of points, you can make this difference very, very small as well. Yeah, okay. So you've already got UPF and LPF very close together. Now you're saying that UPG is kind of tethered to UPF. They can't be very far away from UPF. And LPG is also tethered to LPG. It can't be very far away. So, I mean, if you want to kind of have a visual of this, here's your UPF and your LPF, right? And this distance is less than epsilon over 2. So just have a visual on this assumption. And then what you're saying is, well, what's the maximum distance between UPG and LPG? Well, the UPG can be at most another epsilon over 4 away from UPF. Maybe it's up here. This could be UPG, and this would be, epsilon over 4. And similarly, the LPG can be at most epsilon over 4 away from LPF. So this is another epsilon over 4 here, right? And so then the question is, well, how far apart is UPG from LPG? And the answer is, if you just add up all of these epsilons over here, epsilon over 4 plus epsilon over 2 plus epsilon over 4, you get epsilon. And this is the calculation actually written out in full. So that's how we did that last week. So I'm just giving you kind of the Reader's Digest version of the proof without kind of getting into the nuts and bolts of the refinement that we needed to use, but it's I think good enough for our purposes here. Okay, are you guys with me? So that was mostly done before. I'm just kind of reviewing it. But what we did not prove last time is that these integrals are the same. That I ran out of time for, and I'm gonna finish up this proof now by showing you that part of it, okay? So let's do that little part of it here. So here is the idea. So we have, this is actually very easy. This proving that the two integrals are the same, this is gonna take us no time at all. Let me show you why. I have my L of PF minus epsilon over 4, that's gonna, on the left side, that will be less than or equal to L of PG. Now, let me again just remind you, why is that? We'll take a look here, guys. How far apart can LPF and LPG be? At worst, if we look at LPG, it could be possibly epsilon over 4 away from LPF. Okay, so if I subtract epsilon over 4 from LPF, then that has to be less than or equal to LPG, right? Well, any lower sum is always less than or equal to the integral. Because remember, the integral is going to have any one of those LPGs is going to be a lower bound for the actual value of the integral. That in turn is less than or equal to UPG. And guys, UPG is less than or equal to UPF plus epsilon over 4. You can actually kind of see that partially in this proof here, right? UPG is less than or equal to UPF plus epsilon over 4. So literally the same thing. I'm just recopying it. And the LPG compared with the LPF minus epsilon over 4 is also already kind of baked in over here. So I've just kind of taken all of that and put it together. But guys, here's the deal. Okay, you ready for a big less than or equal to sign? See this thing over here? This L of PF minus epsilon over 4, this is less than, well, let's just do it this way. This is less than L of PF, which is, of course, less than the integral of F, which is less than or equal to UPF, which is less than or equal to UPF plus something. So I'm just making a second pass through this chain of inequalities here, and we get something like that. Okay. But how far apart is this whole entire thing? Yeah, it's so you can see here, I took UPF plus epsilon over 4 and I subtracted LPF minus epsilon over 4. What's the difference between them? Well, I did all of that here. It's less than epsilon, right? So this total distance is less than epsilon. From the far left to the far right, those two numbers are within epsilon of each other. And so if I've got any two numbers that happen to be in between, then they're kind of fenced in. They can't be farther apart than the full width of this entire number line that I've got here. So the distance between these two things is less than epsilon as well. So let's just add that to our notes. I don't know which one is bigger, so let me use absolute values on this. But the absolute value of the integral of f minus the integral of g, right, is for sure less than epsilon. But epsilon was, of course, arbitrary. It says let epsilon greater than 0 be given. So this epsilon could be as small as you want. It could be like almost like you could create a sequence of epsilons that are converging to 0, for example. And this inequality, this absolute difference would be less than all of them, right? So since epsilon is arbitrary, we conclude that the absolute value of the integral of f minus the integral of g is actually equal to 0. And that just means, that just means that those integrals are equal. Yeah. Integral of f equals integral of g. There's your proof. There's your proof. So if you move a finite number of points from a function that's already Riemann integrable, your function will still be Riemann integrable. Make enough sense? And the value of the integral doesn't change. It's pretty nice. It's pretty nice. Let's do a homework problem that uses this. I think I'm gonna do, let's do 6.4 number 1, because it's really easy to do it if we just use this theorem right here. So let me just write it down, because this is one of the ones you guys wanted to see. We're going to let f of x equal, and I'm going to make the function sine of x over x. This would be if x does not equal 0, and 0 if x does equal 0. And so this is just an example, but what we're going to try to do is prove that f is Riemann integrable from 0 to 1. That's what the question's asking us to prove. And I think we can do it pretty easily. Now, if you think about sine of x over x, so let me just kind of draw the interval from 0 to 1 here. Sine of x over x is continuous as long as we're not at 0. So if you think about that actual function, I mean, you could think about sine of x looks like that and x looks like that. So as a fraction, it's something less than 1. But guys, it's something less than 1, but it's approaching 1. And then there's an open circle here. So if I'm just going to kind of be rough with my sketch. Sine of x over x looks something like that. It's got a bigger denominator than the numerator. This is 1 right here on the y-axis. The denominator is bigger than the numerator, so the fraction is less than 1. But it does approach 1 as x goes to 0. That's one of those famous limits that you probably saw in calculus, right? So recall that the limit as x approaches 0 of sine of x over x, that's actually equal to 1. You can prove that using L'Hopital's rule, for example. So typical way that could be done. Or you could use a power series expansion of the sine of x. Doesn't really matter. But the way that this function f has been defined is that f of 0 is 0 right here. Right? So is it possible to move one point on that graph in such a way that, let me just Sorry, let's just make this one right here, right at the end of that thing I drew. Is there a way to move one point on that graph and make it Riemann integrable from some reason that we already know? Okay, yeah, it certainly looks monotone. What's another thing about it that you could say? Continuous, right? Continuous, monotone. Monotone would be, I'd have to take the derivative of it and just make sure it's, not switching from positive to negative. But for sure, it's continuous, except at zero. So you know what we're going to do here, guys, for the solution? For the solution, I'm going to define G, right? I'm going to define G from 0, 1 to R via G of X equals sine of X over X if X does not equal 0. And what could I define G of 0 to be? 1, right? In other words, I can fill in this hole right here. So I could define G like that. And now this function is continuous everywhere because it's, this is two continuous functions divided into each other. Quotients of continuous functions are continuous. And it is continuous now at 0 by the huge remark, right? The limit of sine of X over X is equal to G of 0. Right, so this is now equal to G of 0. So I've got the limit of G of X as X approaches 0 equals G of 0. So that means that thus G is continuous by that huge remark from back in chapter 4. And guys, if G is continuous, then it must be Riemann integrable. That was one of our theorems, yeah? Any continuous function is Riemann integrable. That was theorem 6.7. So let me just add that here. So thus, G is an element of the Riemann integrable functions from 0 to 1 by theorem 6.7. Anything continuous is always Riemann integrable. And therefore, F is Riemann integrable by that theorem, 6.5. Okay, so then F is Riemann integrable on 0 to 1 by theorem 6.5. We'll just kind of put those two things together. Okay, so that works pretty nicely. That works pretty nicely. Questions? Which was the problem that, Litzy, you were asking me about?
The one
In my office hours?
Number 5.
In that same?
6.3.
Oh, yeah. So did you guys do, while I'm thinking about the homework, it didn't end up in my homework help list over there, but I just want to say something. On number 5, this is the one that says, okay, you have, I'm just going to sketch this statement because it's kind of long to write it all the way out. But you have this interval from A to B. And then you're partitioning, there's a partition. Okay, do you guys need help with this? Yeah. Why not? I get excited, I want to do them. So there's your partition. And as you know, this is like x1 and x2. Somewhere along the line, you have xi minus 1 and xi, and then it just keeps going, something like that, right? And what they tell you is that the function is constant on each open subinterval. So, your function is a constant on that open subinterval. And then on the next open subinterval, it's a constant. And then on the next open subinterval, it's a constant. Notice I'm putting open circles on the endpoints because we don't know what's happening right at the endpoints. So this is kind of each open subinterval, the graph is constant, but of course it is defined at all of these other points too. So you would still have, some values here, but you don't know where they are, right? It could be some weird thing like that. That's your function. That's your function. And the first constant value is y1, the next one they call it y2, and then this one is y3 and so on. Right, so those are the constant values. And it says that this is your function f. And they say, show that this is Riemann integrable. So show that f is Riemann integrable on the interval from a to b. So let me tell you how to do this, and I'll see how many details I fill in. I'll probably get excited and do the whole thing. The way to prove that f is Riemann integrable on a to b is to prove that it's Riemann integrable on each individual little subinterval. Because didn't we do a homework problem last week where we said, okay, if I have a function that's Riemann integrable from a to c, and then it's also Riemann integrable from c to b, then it's Riemann integrable all the way from a to c. If I just use that rinse and repeat n times for this partition here, I can prove that f is Riemann integrable on the entire interval by first showing that it's, so in other words, it suffices to show, to prove. And I believe this is by homework number 14, the one we did last week, problem number 4 on that sheet. It was that one that was a handout of 5 problems or whatever. I believe I have that reference correct. Oh, it's homework 15, I'm sorry. Okay, so by homework 15, problem number 4, it suffices to prove that f is Riemann integrable on each of these little subintervals from xi minus 1 to xi. Okay. But guys, if I focus on just one of my subintervals, the function is basically constant. Constant functions are always Riemann integrable. Admittedly, the endpoints of the interval have been moved, but there's only 2 endpoints. 2 is a finite number of points that are being moved. So you can argue that f is only 2 points away from being a constant function when it's being viewed on that subinterval, right? So that's how you're going to do this, right? To do this, note that on the subinterval from xi minus 1 to xi, f is just 2 points from being constant. Okay, and then I'm just going to say, so we have to just write a little essay for this, right? So since constant functions are always Riemann integrable, since constant functions are Riemann integrable, so is f on this closed subinterval, and this is by theorem 6.5. So again, I'm using the same theorem again. So f is Riemann integrable on that closed subinterval, and then you're just gluing together all of those subintervals by using the homework problem from last time. So that's how you show that the function is Riemann integrable all the way from a to b. It does also ask you to evaluate the integral. So this one, there's a second piece to this whole thing. I'll just very quickly mutter something about that, right? So the second part of it is to actually evaluate this integral. And again, by an earlier result, this can be broken down as the integral of f from a to x1 plus the integral of f from x1 to x2 and plus ... plus the integral from xn minus 1 to b of f, right? So you can break this up. I think this is proposition 6.5. That sound right? Okay. Yeah, so you got that. And then guys, how do you evaluate each of these integrals? Again, by theorem 6.5, f is only 2 points away from simply being a constant function y sub I. And we know how to integrate a constant from a to b. That was another homework problem, right? So you can kind of put all of this together. You can change this first integral to simply the constant y1. And then that's just a constant. And then the second integral is the integral of y2. And you just shift all of these over, xn minus 1 to b of yn. This is by theorem 6.5, the actual integration part of it. And I wish they would have called them C1 and C2 and C3. That would have been a little nicer, because we usually use C's for constants. But of course, if those were constants, you would know how to do those integrals. The first one is just y1 times the x1 minus a, which is just delta x1. And then the second one is y2 times delta x2 and dot, dot, dot up to yn delta xn. So this is by 6.1 problem number 1. It was like the very first problem in the first section of this homework, the homework for this chapter. Very first problem. Okay, so 6.1 number 1. And now this is what you wanted. That's what they're asking you to show. So there you go. So none of this is that long if you just use the theorems that they've already given you. That make sense? I like these problems, guys. I do like them. Okay. Let me see where I am here. I got a little carried away. Yeah, so if I give you, and I'm not gonna take any notes on this, but just as this is kind of a rule of thumb. If I were to do something like this, and I give you a function like this, and I ask you to prove that it's, Riemann integrable on the whole interval from A to B. So if I ask you to prove that that thing is Riemann integrable all the way from the left to the right, would you be able to do it? The trick is to chop it up piece by piece. Chop up this whole interval into a bunch of sub pieces and prove that f is Riemann integrable on each piece, either by using continuity on that piece or monotone on that piece. Like here, the first piece is actually monotone. You wouldn't need to actually even use theorem 6.5 on this first subinterval. You could just simply say, oh, it's already monotone. Monotone functions are always Riemann integrable, right? And then go to the second piece, that's also monotone. The third one's also monotone. The fourth one is not. I guess this last interval, it's not monotone and it's not quite continuous. So we'd have to do the 1 point displacement thing and use that theorem for this last subinterval. But you're kind of seeing how you can kind of put these different theorems together and prove lots of things are Riemann integrable. Yeah, that's kind of the idea behind that. Okay, so I'll leave it at that for now on that topic. I wanted to mention a few other things. Go to the right page. We have a lot of results that help us to prove that functions are Riemann integrable, but I want to give you some results about how to actually evaluate these integrals. So let me come back over here and I'm going to state one result right now, kind of a baby warm-up result, and then we'll get to the really good stuff. Certainly by Thursday, we'll get to all of the really good stuff. So there is a mean value theorem for integrals. This is not to be confused with the mean value theorem that we already learned about derivatives in chapter 5, but there is a result here that I want to share with you. So next, let's turn to methods of evaluating the integrals. I want to give you just a few little results on this. Okay, it's not going to be a lot. So the first one is theorem 6.8. And this is the mean value theorem for integrals. Okay? Let's talk about the mean value theorem for integrals here. And so here's what it says. It's a pretty easy statement. If f is continuous on a closed interval from A to B, then there exists a C in that same closed interval AB with the value of the integral. So the integral of f from A to B is actually equal to f of C times B minus A. So there exists a C such that this is true. Just to give you kind of an intuition about this, like sort of a little bit of a geometric insight behind the result, before I prove it, I just wanna see if you guys kind of believe this result. So if I have, my usual closed interval here from A to B, and my function is maybe, I don't know, something like that. So this is f. Of course, what you know is that the integral of f, we haven't presented it this way, but the integral of f is really the area under this curve between A and B. That's how they teach it in calculus. So this area is something that you could, if you imagined that you could reshape and sculpt this space here, you could push down on the left side and kind of smooth it out, move some of this. If this was like Play-Doh or dirt or something, you could like move some of this stuff over and fill in on this side and kind of make it all flat. Use a bulldozer to flatten it off. Well, if you flattened it off, you would turn it into a rectangle, right? So this would turn into some kind of a rectangle here. I'll just draw this rectangle, and the area of that blue rectangle, I don't think I did a very good job, because all of this has to fit right there. Sorry, something like that. But the point being that this rectangle has a width of B minus A. And the height of that rectangle is actually equal to f of C, if that was my C right there. So the height is just f of C, and we all know that the area of a rectangle is just the height times the width, right? So that's the right-hand side of the mean value theorem here. And this is kind of the visual that goes along with that. Okay, so there's a little bit of a geometric insight there. Does that make sense? Yeah, so you're just smoothing off the function kind of to whatever its average height would be, right? So another way of saying it is that there is some C that achieves what I would call sort of an average height of the function across that whole interval. Okay, so that's one thing worth mentioning. The other thing I thought before I do the proof, the other thing I thought I would show you is that it is absolutely critical that the function be continuous. So this won't be true if the function isn't continuous. Let me just show you that as well. So just as a quick little example, the mean value theorem for integrals fails if f is not continuous. I think I'd like to convince you of this a little bit as well. Let's just suppose that we have, this time let me pick, so for my example here, let me just pick something very explicit. Let's suppose we go from 0 to 2 on the x-axis, and I'm gonna cut it up in half here, so it'll be a 1 halfway along. And then the way to make a nice counterexample is to just, I need something that's not continuous, but I'm not gonna go hog wild and do something super weird. I'm just gonna make a constant function over to 1. Right, so I'm gonna make my function look like that. This could be 1, in fact. And then I'm gonna jump it up to 2, and then step, it's like a step function, right? So you just take the next step up, and then we go from 1 to 2 like so. this would be an example of my function, so this is f. So formula here is, f of x equals 1 if x is between 0 and 1, and then it equals 2 if x is between 1 and 2. So that's the formula, piecewise defined formula for f. And the actual value of the integral, so here, the integral from 0 to 2 of f is, well, I'm gonna use the theorem that says I can break it up. It's the integral from 0 to 1 plus the integral from 1 to 2. And between 0 and 1, the function is essentially a constant with 1 point displaced. But again, moving 1 point, that earlier result, moving 1 point doesn't change the value of the integral. So this first integral is really just 1. And then the second integral has again, a constant value of 2. And so the value here would be 2 times 1, which is 2. So the whole thing is 3. Guys, literally, we're using the homework problem. Essentially just using this problem we just went over. I'm kind of using that to do this integral right now. So we get 3, right? And so this is a 3 right here, and b minus a is 2. Because b is 2 and a is 0 here, right? So here, a equals 0 and b equals 2. So the integral from a to b of f divided by b minus a, if I just divide by b minus a, it would be 3 over 2. And 3 halves, well, 3 halves is right about here. Is there a c value that hits 3 halves? There does not exist a c such that this is equal to, so this does not equal f of c for all c in the interval 0 to 2. So yeah, we cannot make that work. So it fails if the function is not continuous. Okay. Is that clock right, by the way? It is, yeah. I feel like I've been talking for 3 hours. It's only been an hour.
Yeah.
Okay. Whatever.
You have off time before this.
I think that was it. Yeah, I was pretty busy this morning, that's for sure. Okay, any questions so far? Let's do the proof of this and then we'll take a break. Okay, the proof is very short. This is a pretty easy one to prove. So we'll just do that really quickly and then we'll take a little break. Guys, we are in this very favorable situation of having a continuous function on a closed interval. So that means that all of our consequences of continuity can be used. Specifically, I'm going to use the extreme value theorem to say that well, actually, I'm sorry, I'm going to use the fact that the function is bounded. So a continuous function on a closed interval will always be bounded. And so we can use that to help us with this proof here. So let's try it, guys. So since f is bounded, sorry, I want to get the number of that results. That's what I wrote in my notes, but I actually think it's proposition. I think I wrote the wrong number down in my notes. 1 second, let me find this thing.
It's continuous on AB and F has an absolute max and absolute min.
Yeah, it's not the one I'm using. It's proposition 4.8 directly above that. I wrote the wrong thing in my notes. That's why I got confused. Sorry. Proposition 4.8, since f is bounded, if we take the infimum of the set of the f of x's, where x is in the closed interval AB, this will be a real number. I'm going to call it little m. It will actually be a number little m. And the supremum of all of the f of x values, we're going to call that capital M, and that's also a real number. Okay, so both of those exist as real numbers. No worries there. Okay? So, in other words, the highest value that the function ever reaches is capital M, the lowest value is little m. So if I actually look at little m times b minus a. So again, it'd be kind of like taking the infimum on this function, you'd be right here, and the little m would be this value. And what you can do, guys, you can make a little rectangle here, which is going to be underneath the area under the curve. So that's what this area is, right? The little rectangle has a height of little m and a width of b minus a. Guys, that will be less than or equal to the actual area under that curve, which is what the integral of f would be. By the way, this integral exists because the function is assumed to be continuous. Continuous functions are always Riemann integrable. Whenever I write this symbol down on my paper, I have to do so knowing that the function has an integral. So I shouldn't be writing this kind of thing down. It's like I see in my 250B all the time. People will write down inverse of a matrix, and I'll be like, oh, is the matrix invertible? Because if it's not invertible, you can't write that down. So the same thing here. If the function's not Riemann integrable, we shouldn't be writing this kind of thing down in our proof. But we do know that f is Riemann integrable because it's continuous. Okay, and then this will be, as you could probably expect, less than or equal to capital M times b minus a. Okay, so that all of that is pretty clear. And so what I'm going to do next, guys, is just divide everything through by b minus a. So little m, it will be less than or equal to the integral of f over b minus a, which will be less than or equal to capital M. Okay. We're almost done. This is a short proof. We only have about one more line to say. So guys, my function hits this number, it hits this number, and so it will also hit every number in between those two numbers, including this one. That's the end of the proof. That's by the intermediate value theorem, right? So there'll be some points S and T where little m and capital M are achieved. And then you can just make this interval from S to T, and the f of S and the f of T will be these two values. And then you have that closed interval that you can apply the intermediate value theorem to. So I'll just make this very brief. By the intermediate value theorem, which again, we can use because the function is continuous, there exists a C in the closed interval AB with f of C equal to the integral of f from A to B all over B minus A. So you've got your little m, you've got your big M, and this integral divided by B minus A is somewhere, sorry, the little m is actually the y value, and the big M here is the y value, right? So you've got these two y values. The integral divided by B minus A is somewhere in between. And so there will exist a C within that interval where you actually hit that intermediate value. That's your IVT. Okay, so that's the end of the proof. Questions here? Well, I should point out that this is not a great way to evaluate integrals, because you probably aren't going to know what C is, right? It just says there exists a C. If we knew what C was, sure, we could evaluate it, calculate B minus A, and that would give us our answer. But if we don't know what the correct C value is, which this theorem doesn't really tell us, then you can't really use it very well to evaluate the integral. So I'm not going to toot my horn too strongly about this result. This is just the warm-up. What's the big result that we use to evaluate integrals?
the fundamental theorem of calculus, which is really the one and only thing we have not done yet. So we have to do it this week. When we come back from taking a little break, I might look at some more of the homework questions, but beyond that, we've got to get to these two fundamental theorems this week, kind of the big climax of real analysis, which I'm super stoked about. So in the meantime, let's take 10 minutes, let you guys stretch your legs, grab some fresh air if you'd like, and in 10 minutes, we'll pick things up.
I know. That's ridiculous. Oh, he's like, I don't have my handphone. Never show me a handphone. Show me a handphone.
Prove it rigorously,
Mhm.
please.
Why is it? To see what it did that I was going to.
What is this?
Oh, stop sign. That wasn't even so nice. Oh my gosh. Before you saw me. Yes.
You're looking forward to not having to work the lectures?
No, it's not you. It's everything. I'm taking 4 math classes.
I know, you're
and
tired.
It's not you.
We're all, I'm tired.
But then I have to go back to the kids.
Got it. What's the flight?
No, start it.
So pretty people.
But I thought you were obviously no, exactly. You were writing that up. I didn't see the number 10 and I was like, that looks so familiar.
Oh, I wonder why.
That was the question that I asked.
Did you put it on the board?
I asked Lindsay to put it on the board.
Oh, okay. Well, it's on the board.
But it was just funny because I was like, that's like the question that I was wondering. about.
Yeah, that's a good one. I like these problems, actually. It's kind of a nice set.
You like all the problems.
I
that you're getting.
do. I get excited. What can I say? Okay, just gonna decide if I want to answer that kind of thing right now. Yeah, you can ask me. Yeah, but
I mean, honestly, like,
it's like you needed to say that this limit exists in R. Because if it doesn't exist in R, then this could be something like infinity or something that's indeterminate. So it's the fact that F is differentiable that means that F prime of C is a real number. It's not infinity, it's not minus infinity, it's not DN, it's actually a real number. And once you know that, then obviously from this step to this step is fine. But then if both of these limits exist, then you're allowed to use this limit property. So those properties of limits They only work if the individual limits exists in the first place. So you just needed to talk a little bit more about that. Okay, but the actual steps you're laying down are all correct, but there needs to be a little justification. Yeah, that's it. Sure.
No, I'm not, no, it's not gonna be done. There's no fire.
Yeah, go for it.
Not even you. I was. Hmm. Okay, so-
Sometimes I'll be threaded. She likes to make things.
Mhm. It's funny though, because like, my husband wears jeans all the time, she won't touch it. Doing nothing,
It's just like.
but as soon as I wear jeans, I'm like. No, specifically my. I love that we went from Koshi, I went from Koshi and 350 to Koshi Swords and 307 to now. What is this Koshi? Like
It's just Koshi
Kowalski Schwartz.
Is that still
It's,
good?
it's still just good.
I was like, it just keeps getting longer, Koshi's always in here.
Alright, we just have to go with Suchava, there's gonna be on the final two.
The Koshi Schwartz, he loves
Yeah.
that. He loves that.
Koshi,
I watched him
Nesbitt.
give so many talks, he always brings that up. So I would definitely, if you're in his class, I would definitely know.
PowerPoint. His finals on Thursday, so he have 3 days to dedicate. 3 days to dedicate to you.
Nice.
Yeah,
Thursday of next week?
Next
Yeah.
week, yeah.
Okay.
Dr. Ashley brought it up, when we were in 402, she's like, how many of you took 417 this year? You wanna raise your hand? She's like, so did you guys do triangle similarities?
We didn't do it with.
Nope.
With Rathbun, but.
Rathbun did not do it, he skipped 5 chapters to get to what he wanted to talk about.
Didn't really talk about it.
We were spent so much time in neutral,
You see, with Suchava, we hardly did anything.
we spent so much time in neutral,
We're doing, I was at the beginning, like Lydian plane and circles.
and then we skipped over everything else to the point where you just.
We didn't do, six.
No, we started doing the
Six
reflective.
quads.
No, we didn't.
Yeah, always, it's Charles. The best is.
We did, what were we doing? We were doing the point query list and then the reflections and all that. Chapter 11.
But we're doing more like the platinum and the monthly math problems.
Oh, that's like the one that he said if you solve this, you get extra credit, but it
Yeah.
hasn't even been solved yet.
Yeah. He was like, we asked him today, because he was gonna say something, he's like, I can figure it out.
How was your weekend? Oh, tiring. Tiring?
Yes.
Yeah, stuff going on.
Yeah. Working.
What was my weekend? Yeah, and office hours, I, did all my, well, yesterday I did a bunch of errands. Over the weekend, I just had to take it easy. I had to do all my grading on Friday.
I
So,
wish I'd gotten thinking.
yeah, it's been kind of a busy time. I had to write my midterm for my other class, which I did this afternoon. Takes a long time to do that.
And it's 4 more weeks.
We're almost there, yeah.
And then
Sucks because it's Mother's Day this weekend, again.
It always falls right before finals. I hate that. Yeah, I hate that too. Every year they do that.
Then Mexican Mother's Day is on Saturday,
Oh, man, the whole
so it's
weekend.
like, it is Mother's.
Darren, be back. Oh, he's not quite back yet. Well, you tell me, I actually think I talked to him about this one in office hours, so I might just go ahead. Let's just get into it so that'll give me a little more time to do stuff. So this is, one of the problems that was up on the sideboard, so, let's try and prove this one. This one is, a very sort of computational type of example. So if we start with two Riemann integrable functions f and g, then we don't have a nice formula for the integral of f times g, right? We can't just split up like we can with addition or pull out scalars like scalar multiplication. This is multiplying two functions together. So we don't have like a nice theorem for that. So instead, we're gonna settle for some kind of an inequality here. And so that is what this question is asking you to do. And they have a pretty big hint on how to do this problem in the book, and the hint is exactly on point. It is a very good suggestion, which is that they ask us to expand the integral from a to b of x f plus g quantity squared. Now, before I do that, before I actually expand it, I just want to point out this function is greater than or equal to 0. Which means that the integral, if this function is great, because it's a square. You're squaring a bunch of numbers, then they're always above the x-axis. If you're integrating a function that is greater than or equal to 0, then the value of that integral is definitely greater than or equal to 0. So we do know that. We do know that. But anyway, so we're gonna use that in just a second. Now I'm gonna actually do the hint, which is to expand this integral, right? So what we have, maybe I'll start with the 0 on the other side now. So 0 is less than or equal to the integral from a to b of xf plus g quantity squared. By the way, that x is just a parameter. It's to be viewed as some fixed value, okay? So just treat that as a fixed parameter. And what I'm gonna do now, guys, is inside of this integrand, I'm just going to actually expand it out. So I will get x squared f squared plus 2xfg plus g squared. I'll get all of that stuff, okay? And again, if I'm treating the x as a constant, as a fixed parameter, I can pull it out of an integral. I can also split up the plus sign here. So I'm gonna do a quick little algebra manipulation using properties of integrals that we've learned previously. And write that as x squared times the integral of f squared plus 2x times the integral of f times g plus the integral of g squared. We'll start out writing it like so. Okay. And this can actually be viewed now as like a quadratic equation. Like, so if I treat so I'm gonna make a little, over here, I'm gonna make a little change of variables. I'm gonna let capital A denote the integral of f squared. And I'm going to let capital B denote 2 times the integral of f times g. And I'm gonna let capital C, this is just notation. I'm just making this notation. C is gonna be the integral from a to b of g squared. So I'm just going to adopt those changes of variables so that I can now write this as ax squared plus bx plus c. And this is a parabola. It is a parabola that is always greater than or equal to 0. So if I was going to draw the parabola on the x-axis, and then I could call this the y-axis, right? This is a parabola that it is going to be oriented upward because a is the integral of a positive function. So it is oriented upward, but the entire value of the output is at least 0. So your parabola is like something like this, right? If you were actually thinking about the graph of this thing as
as a parabola, it would look like that. And what that means is that this has no real roots. Right, so this parabola has no real roots, so thus, ax squared plus bx plus c has, I guess I should edit that because this does say greater than or equal to 0. So this parabola could potentially come down and touch the x-axis in one single point, but it can't touch it twice, right? It can't go below, it can't actually dip below the axis. So this has at most one real root. It's kind of a clever argument. We do know how to find the roots of a quadratic though. The roots are x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And in order for this to not be two real roots, the b squared minus 4ac has to be less than or equal to 0. So, because if b squared minus 4ac was positive, then you would actually get two different real roots. And we're saying no, this thing has at most one real root. Okay, so the roots are that, and so from this, we conclude that the so-called, this is what the hint talks about, the discriminant, which is b squared minus 4ac, it has to be less than or equal to 0. And now let's replace the a, b, and c with what they actually are again. So b squared is, 2 times the integral from a to b of fg. That thing squared, and I'm gonna move the 4ac to the other side, less than or equal to 4 times a, which is the integral from a to b of f squared, and then c, which is the integral from a to b of g squared. So like that. Let me move my camera over to the other side. And you can cancel a 4 from everything there, right? There's a 2 squared on the left and there's a 4 on the right. So I'm going to cancel that. And so what's that going to leave me with? So that's going to leave me with the integral from a to b of fg squared is less than or equal to the integral from a to b of f squared times the integral from a to b of g squared. And so how do I get my final?
Square root.
Yeah, take square root of both sides, because this is what I'm trying to prove. That's what I'm trying to prove. So now take square root. Taking square root, we will get the integral from a to b of fg. Actually with absolute value, right? Because if you take the square root of x squared, that is actually the absolute value of x. And on the right side, we're just gonna throw a radical on top of everything here. So the integral from a to b of f squared times the integral from a to b of g squared. And that's exactly what we wanted. That's exactly what we wanted. Yeah. That look okay? So it's a little trick. We use this x parameter to kind of create a parabola. And the coefficients of that parabola are related to the things in the problem we're proving here. Yeah.
So, how did we do that x squared, the line item
From here to here.
there to there?
So remember that x is just being viewed as fixed.
Oh,
So I'm viewing it as a number that I can pull out of this integral as a constant. I know eventually we view the parabola later as not being, we view the x as being allowed to be any value in this parabola, right? This graph, obviously x can be moving around. But in the moment that I'm doing this step, I'm viewing that x as being fixed. Yeah, as like some constant. I almost wish they wouldn't have called it x. Because you generally think of that as a variable, but it's really to be thought of as a fixed parameter. In the moment of this calculation here, yeah. And then, once we get down to here, we say, okay, x could have been anything. And so I can create a function of x now, which is this parabola. And then that parabola has roots, so we can start looking at the roots of it. There is something about this problem, though, that should concern us. It's not really about the proof that we just did, but about the question itself. It's a little bit problematic. And that is that we have two Riemann integrable functions. And I mentioned this earlier today. We should not be writing down an integral of a function unless we know that that function is Riemann integrable. Did we ever prove that if f is Riemann integrable and g is Riemann integrable, that then f times g would be Riemann integrable?
No, I was looking for that actually.
I
to
don't
do this
think so.
problem.
We proved that f plus g is Riemann integrable,
And a
and
constant.
a constant times f is Riemann integrable, but we never proved that f times g is Riemann
I
integrable.
was gonna ask, like, if g was the constant function, then wouldn't that just be a special case of? Like,
You certainly could apply this to a
Right.
constant function, yeah. Yeah, you definitely could, that would be a special case of it. But yeah, let me address this issue, let's go back and take a few notes again. So I'm kind of going back and forth between the homework and the notes. I want to address this issue about the product of two Riemann integrable functions, because I've never said anything about that. Right, so we need to do that, turns out, so let's go back to our notes, guys, wherever you're taking your notes, I'm gonna make a quick lemma here. And here's the way the lemma starts, if f is Riemann integrable from a to b, then, so let's forget about f squared, let's forget about f times g, let's just do f squared. So f squared is Riemann integrable from a to b. And you can see that even that is kind of being talked about in this problem. So we would technically want to know this result. We would want to know that this is true. That if you take a Riemann integrable function and you square it, that it is still Riemann integrable. So I looked at the proof in the book. It's very long. It's very technical. So let's see, we've got tautology. Proof by postponement, maybe? Proof by calculus. The proof requires calculus, so we'll skip it.
That's a good one.
I like that one.
Yeah.
Insert trick.
So I am actually going to admit this one. I read the proof through and I thought, this is really long and technical and it's not that enlightening. So it is spelled out in the book fairly carefully, but this is one that I'm not going to expect you to know about and we're not going to do it. I'm just going to take this as kind of a freebie because it is so long. If I stop and prove this right now, we aren't going to get to the fundamental theorem of calculus, and that would be almost a crime. So I'm not going to let that happen. So we'll omit this and we'll find any number of things on this sheet, front or back, that we can use as a justification. I'm sure there'll be something there that would be amusing enough to count. But yeah, I am going to omit that one. But then using that lemma, we can now prove a more substantial corollary, which is really what we were after. So the corollary here, corollary, or I don't know how you say it. So 6.1, so this says if f and g are both Riemann integrable on AB, then, and there's actually three parts to this. The first part is that f times g is Riemann integrable on AB. So this is really where I kind of started this little conversation. F times g, and then secondly, we should also have absolute value of f. That's another one. Absolute value of f is Riemann integrable from A to B. And there's a second statement here with this, which is also kind of nice to know, which is that if you take the absolute value of the integral of a function, it's always less than or equal to the integral of the absolute value of the function. So if you slip absolute value bars inside your integrand, you make the integral larger. Kind of makes sense, because on the left side here, the function could be positive, negative, and all the area cancels out to 0. On the right side, no, everything has been replaced with a positive absolute value of f, so you're only going to contribute a positive amount of area to that. So this is certainly a reasonable thing to expect, because the left side has a bunch of canceling going on, the right-hand side, nothing is canceling, it's just piling on positive. Okay, and then the third part of this corollary is that if you take the maximum of two Riemann integrable functions, f and g, that is Riemann integrable, and the minimum of those same two functions is also Riemann integrable. Okay, so that is the corollary. So we do get some nice results about how to combine f and g in other ways that we hadn't talked about before. Let me see how much of this first I want to do. Oh, I love it. I told you about that journal article I got to review one time, right? Where they kept referring to some other thing I couldn't find. It's like, I think they're trying to pull a fast one on me now. Anyway, no, so this one I will try on part 1. This is super easy now, if you're willing to believe the lemma. Right, so this, you have to believe the lemma. So, well, where's the one about? Oh, proof by necessity. It had better be true, or the whole structure of mathematics will crumble to the ground. I love it. Yeah, so that lemma better be true. Otherwise, this isn't going to work. But we're gonna try it. So here it is, guys. It's very easy. If we just take f times g, we're trying to prove that this is Riemann integrable. All we have to do, guys, is rewrite it in a way that is based on other functions that are already Riemann integrable. So just check this out with me. If we take 1/4 of the quantity of f plus g squared minus f minus g squared. So first thing I want everybody to do is do the mental algebra with that and convince themselves that this is correct. So the f squared and then minus f squared, that cancels. G squared minus g squared, that cancels. What's the cross term? Well, I've got a 2fg, and here I also have a negative 2fg, but I'm subtracting it. So it's actually 4fg. Put a 1/4 in front of it, you get fg. Now guys, everything on the right-hand side is taking f and g and doing addition, subtraction, squaring, and a scalar multiple. All of those operations are already Riemann integrable, so that means that this thing is Riemann integrable as well. It's a combination of things that are already Riemann integrable. So since the right-hand side, I'll write that as RHS, is a combination of Riemann integrable functions. So we are combining them in ways that we know that we can. Okay. For number 2, oh gosh, I am going to do this number 2, which is the absolute value of f as well as that inequality. I am going to do that in my review sessions this weekend. So again, I'm just going to say see review sessions.
for the final. It's a really nice example to do, but I just want to save a little time right now. I will come back and do this. I'm not trying to pull another one of those,
Not omitting.
I'm not omitting the proof this time. I'm just postponing the proof by postponement, which is somewhere on here too. Right, so we'll postpone that one for now. It's a nice one. And then the third one now becomes very easy again. So if we just assume enough things, then we can prove whatever we want, right? So the max of f and g. So here's what you have to convince yourself of, guys. To write the maximum of two functions, what you first do is take the average of them. So you average the two functions. And then you have to, if you're halfway between the two functions, then you have to add the other half between them to get up to the maximum one. So you add half of however far apart the functions are, which would be absolute of f minus g. So if I want to know the maximum of even just two numbers, if I want to know the maximum of two numbers, has anybody seen this in some other place? Right, so if you want the maximum of two numbers, just take their average and then add half of the distance between them. You'll get to the maximum. So there you go. And on the right-hand side again, what do you have? You have scalar multiples, you have addition, you have subtraction, and now you have absolute value as well. So we are now relying on part two. Part two says that the absolute value of anything that's Riemann integral is still Riemann integrable. So this is Riemann integrable on A to B, since the right-hand side is a combination of Riemann integrable functions. Right, okay, so, oh, and then the min case is similar. I won't write it out. It's basically the same idea. So the min of f and g, for that case, this one is just similar. So we'll take advantage of that and not repeat ourselves too much on that. Okay, awesome, awesome. Questions about any of that? So you can take two functions and that are Riemann integrable, you can add them, you can scalar multiply them, you can subtract them, you can multiply them, you can take absolute value of them, you can take max or min of them, all of that works great. Some of you still might be out there wondering, well, what about dividing them? Because I haven't said anything about that. Turns out division doesn't work. Because actually, if you take f of x divided by g of x, you might not even have anything that's bounded anymore, right? That g of x could be very close to 0, which would mean that f of x over g of x is blowing up to infinity. So we're not going to have, you're not going to see a result here about f over g. But everything else has pretty well been addressed here. Okay. We all good on that?
So if we were doing the main case, we would just be subtracting half.
Yeah. For the min case, you literally just replace this plus with a minus. Yeah, that's exactly how it works. Yep. Other questions? Well, I think we're gonna wait till Thursday for the really big punchline, which will be the fundamental theorem of calculus. But before we do that, we've got a few more minutes today to look at a little. So I did number 10, right?
Yes.
So the one that goes with number 10 is number 12. So let me just, as long as I'm thinking about it, let's just look at number 12. Back to the homework again. I hope I'm not making you guys too dizzy. We're gonna do problem 12 together here. I'll help you with this one. So this says that, so this basically says show that the square root of the integral from a to b of f plus g squared, right, is less than or equal to the square root of the integral from a to b of f squared plus the square root of the integral from a to b of g squared. So this turns out to be a totally computational problem, but we're going to use the result over here in a minute. Okay, so for the solution,
I just wanna expand this out again inside this integral, so starting from the left side, I'm just gonna go ahead and start on the left side here. The integral of f plus g squared, and then we have a radical over the top of all of that. So I'm just gonna expand what's under this integral, so it will be the integral of f squared from a to b. And then plus 2 times the integral from a to b of f times g. And then plus the integral from a to b of g squared. So just using the property of integration that it respects addition and scalar multiplication, I can just kind of expand it out underneath the radical. Look all right? Now, what I can do next is I'm gonna now do a less than or equal to. I'm just gonna replace the integral of fg with the absolute value of the integral of fg. And I'm doing that because I can see I want to get it into a friendly form to use the earlier problem. So just a real short little step here, guys. All I'm gonna do here is replace the integral with the absolute value of the integral. Okay, so we'll have something like this. Okay, so just replace the integral with the absolute value of that integral. That only makes it bigger, right? That only makes what's underneath that radical larger. And now I'm gonna replace this absolute integral of fg with the right-hand side here, okay? So let's do that. This is also less than or equal to, this is by number 10. So we're using problem 10 to do number 12. So this becomes the square root of the integral from a to b of f squared plus 2 times, oh boy, the square root of the integral from a to b of f squared times the square root of the integral from a to b of g squared. And then finally we have plus the integral from a to b of g squared. Okay. You guys with me? What? If I just call, so if I was to just, again, maybe I'll use A and B, but if I just call A the square root, this is not the same thing that I did in the previous problem, but I'm just gonna use this notation here. If I just call A the square root of the integral of f squared, and I just call B the square root of the integral of g squared. If I just adopt that notation, then what do I have here? Then what I have is the square root of a squared, right, plus 2ab plus b squared. That's all it is. Does that look like something you can do anything with?
A plus b squared.
Yeah, this is, so this becomes the quantity of a plus b squared. And it's under a radical, so that just turns into the absolute value of a plus b. Now, you don't really need absolute value bars though, because a is positive and b is positive already. These are integral square roots of positive integrals. So this is just a plus b. In other words, it is just the square root of the integral of f plus the square root of the integral of g. That's all it is. That's what you're asked to prove. Is that right?
F squared, G squared.
Oh, f squared g squared. Yes, I'm sorry, I forgot to square these things in here. Yeah, thank you. Thank you. Yep. It's good to me. Everybody's getting this down?
Dr. Anna, when we did the by number 10 step, we just used that top part, right?
This is number 10. That's the statement of number 10, right there. We're sticking that in right in that one spot. Okay. That look okay? I'm doing a lot of your homework for you. So I'm sort of selfishly motivated on this because I want to make this easy grading. So that does depend on everybody getting it down correctly because I will be checking it. But at least I can try to be helpful. It also frees up more of your time to be like starting to learn your proofs, thinking about the final and all of that. So I am definitely motivated to help you guys finish this so that you guys also can move on. So there's one, that was number 12, right?
Yeah.
Okay, so then, I have like 9 minutes and I bet that'll be enough time. Let's talk about 9B, is that?
Yeah.
Okay, 9B is the last one over here. And this one says, okay, so let F be Riemann integrable from negative A to A. And then, so assume also that F is an odd function. So assume F is odd. So just to remind everybody, that just means that F of negative X is equal to negative F of X, right? That would be for all X in the domain. And so then they're gonna ask us to prove that the integral from negative A to A of F is actually 0. Now, does it at least make sense though? It should be true, so if I have, let's get this out of my way here, so if I have like, a function that's doing something here and then it reverses it over here, the total area from like negative A to A should cancel out to 0. That's negative and then that's positive and then kind of balance and cancel. That's the idea behind it. So, of course, what we can do is we can say, so note, I'll just start off with this. Note that the integral from negative A to A is just, we have proposition 6.5, which says that I can integrate from negative A to 0, and then I can integrate from 0 to A. So I can break down my closed interval into 2 parts. And so it's really enough to show that this integral cancels this integral. Right? So we need to show, let's maybe just write that down. So we need to show that the integral from negative A to 0 of F is just the negative of the integral from 0 to A of F. Okay. Back over here. All right. So, let's talk about those integrals. We don't really have a lot of results that we can use on this, other than to say that, so we know that, let me just talk about the integral from 0 to A of F for a second. This is, of course, equal to, the upper or lower Riemann integral, right? That's, if a function is Riemann integrable, it means that the lower and upper Riemann integrals agree with each other. So the upper Riemann integral, if you remember, this is the infimum of all of the upper sums, where P in this case would be a partition from 0 to A. That's what it would be. Does that make a little bit of sense? And here's the key idea, is that if you, I'm going to draw another picture over here on the side. So here's 0 to A. You've got the part of the function over here, and you've got some partition here, right, that's creating one of these upper sums. Well, what you can do, guys, is you can define a negative partition, which just puts minus signs on all of these tick marks and gives you a sort of a reflected partition of negative A to 0. Right? And let's just think about this for a second. The upper sums are doing the big MIs of each of these subintervals, right? The capital M's or whatever they are. Those capital M's, if I use the reflected partition on the left side, they will be the little m's of the negative partition on the other subinterval. Yeah, so I can think of this as you know, the same thing as the infimum of, what I could do is I could take the lower sums of negative P of F such that negative P is a partition of negative A to 0. Now, of course, I need to put, so this is the lower, this is adding up a bunch of little mi delta xi's, but those little m's are all negative compared to the big M's that were on the right side. So what is this all gonna add up to? It's gonna add up to the negative of whatever the upper sum would have added up to from the original partition. Okay. Now, I don't know if you guys remember, but way back in like February, when we were first learning about imps and soups and stuff like that, we had some properties about, you know, if I took a set and I had the infimum or supremum of that set, what would happen if I, you know, added two sets together and took the supremum of that or infimum of that or whatever. And there was one for this as well, and we can kind of see it's relevant now, because there's a minus here. The infimum of negative s turned out, if you recall, it was the negative of the supremum of s. So it just flips. So if you take all the values of negative s and you change the sign of all of them, then whatever the greatest lower bound was becomes a least upper bound, right? But then you've effectively changed the sign of everything. So you have to put this little minus in here. So I'm gonna turn this, guys, into a supremum. The imp is gonna turn into a sup, but I need a minus also, sorry, I need a minus the supremum of whatever the set was. This is L of negative PF, such that negative P is a partition of negative A to 0. Yeah. And let's just think about this for a second, guys. Up here, when I did the infimum of all of these partitions from 0 to A, would you agree that if I do the negatives of all of those partitions, I actually get every partition of negative A to 0? In other words, there's a perfect correspondence. If I have a partition from 0 to A, it uniquely associates to a partition from negative A to 0 by just putting minus. I should have defined this here, guys. We should have had this in our solution. So P is, you know, the usual thing, x naught, x1, x2, up to xn. Right? So I should have said negative P is just the partition from negative xn to negative xn minus 1, dot, 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 down to negative x naught. Right? So it'd be something like that. But my point is, guys, here, what my point is that this is the negative. It's the negative of the supremum of all of the lower sums from negative A to 0. And that, by definition, is the lower Riemann integral of f from negative A to 0. Oh, this is so clever. You see that? We're taking the supremum of all of the lower sums. Don't let this negative sign fool you. It's not like literally taking a negative in anything. It's just literally doing, if this is my partition of P, then this is just the partition negative P, right? And so now what is this? Well, this is, we don't need to write lower sum there. We can just write the integral from negative A to 0 of f, because remember, this is Riemann integrable. F is Riemann integrable from negative A to 0, so the lower Riemann sum is the value of the integral. And is that not what we needed to show? So I have the integral from 0, I started with the integral from 0 to A of f. I proved that it was the negative of the integral from negative A to 0 of f. It's exactly the WNTS over there. Isn't this beautiful? So you've seen me do a few little tricks, right? You know, in the review session for the third exam, we did a case where we had a partition from A to B and we added C to everything. It just shifted everything over. Now here's a problem where we're taking a partition from 0 to A and we're flipping it over, right? We're flipping it over so it's now covering the interval from negative A to 0. It's really clever. And by the way, if you preferred, you could have started here with the lower Riemann integral of f, which would have been the supremum of the lower sums, and you could have just kind of worked this the other way around. All of the similar analogous steps would have carried you to the point that you needed to get to at the bottom as well. So either way actually works really nicely. But this is a key fact that I think this was in the homework, but it was like 10 weeks ago at least. So, any questions, guys? Did I leave any of the homework problems for you guys to do?
No.
You still have a couple more to do. 13 is a quick one. Just use number 12, I think. So I will let you do that. So I'm hoping we can give everybody a really good score on this assignment since we did so much of it. But I don't have anything else for today. However, Thursday, a fundamental theorem of calculus, both parts. That's gonna be the main thing we're gonna do in whatever extra time we have. I have a group work and we'll study for the final. So I'll look forward to seeing you then. That'll be our last, and we'll take a class picture. So don't miss it.
Oh.
Want you to be here. I to always remember everybody in my classes. So I will see you then. Bye for now.